Hello again, physicists. So in class, you asked for it, and Mr. H will deliver. You said, Mr. H, I want to see a video where you are using vectors and you are doing either vector addition through resolving a vector or breaking a vector into components. Show us more of those examples, make them complicated. Well, I am delivering on that promise right here. So this video is all about complex vector math. In here, the procedure will be the same throughout. I'm going to break vectors into their components. Once they are in their component form, I'm going to add together those components, keeping in mind specifically that all vector components pointing in the x direction will be added together, and all vector components pointing in the y direction will be added together as well. And that is determined based on my coordinate system. Lastly, whatever I have after completing step 2, I will recombine those into a single vector with magnitude and direction should it be called for. So without further ado, let's get started. Our first example will take us way back to when we were talking about displacement. If you recall, displacement is a vector. And all of this vector math I'm showing you will work for any vector in physics, such as forces, displacement, acceleration, velocity. If it's a vector, this procedure is applicable in theory to it. So we have Johnny, and Johnny is walking 30 meters at an angle of 60 degrees. After doing that, he then will turn and walk 5 meters east, then 6 meters south. We want to know what is his displacement. So to begin, let's draw out the different stages of Johnny's motion, beginning with this 30-meter leg, which is at a 60-degree angle. And there it is. So I've noted, oops. Let's try that again. Here we go. So there is my first step of my journey, which again is 30 meters at an angle of 60 degrees. Next, he's going to move 5 meters to the east. So starting where my first leg ended, I'm going to draw a second vector pointing to the east. That is 5 meters. And lastly, he turns and goes 6 meters south. So there we can see the entirety of Johnny's journey. The first thing I'm going to do here is I automatically, right off the bat, can tell that if I use my standard coordinate system, this vector right here from that first leg of the journey will cause me trouble because it is not pointing strictly in the x direction. It is not pointing strictly in the y direction. It is doing both. It is pointing in the positive x and the positive y direction at the same time. Therefore, I need to break that vector into its components. How would I do that? A little bit of trigonometry. That's how. So in red, I have my original displacement vector. And then in blue, I have the two components, my x component pointing in the positive x direction and my y component pointing in the positive y direction. If I wanted the magnitude for each of my components, the x component would be 30 times the cosine of 60 units of meters, and then my y component would be 30 times the sine of 60, also with units of meters. So what I'm going to do now is essentially I'm going to ditch my original displacement vector and I'm going to replace it in my picture with these two blue vectors. Here's what it'll look like after doing that replacement. So we say bye-bye to that. And here we go. So we'll have my two component vectors, and then we'll have the 5 meters to the east vector and the 6 meters south vector. So let's just label all of these so that we can keep track of them. And this would be 30 cosine 60, and this would be 30 sine 60. So there you go. Here are the two legs of my journey from before, and those are just fine as they are since they are pointing strictly in the x or y direction. And then here are my two components from that first vector. Now you can see that we do have two components where one is strictly pointing in the y direction, one is strictly pointing in the x direction. I can now move on to step 2 where I just add together all my x components and I add together all my y components. I find it's actually nice to make a little grocery list where I can keep track of all my x and y components and how they'll add together. So for the x component, I have 30 times the cosine of 60. And if we got that as a number, it would come out to about 15 meters. And we're going to keep that positive since it is pointing in the positive x direction. The only other x component in this problem is the 5 meters east, which would also be in the positive x direction, so that will stay positive as well. And then in the y direction, we have two y components to keep track of. We have the y component of our original vector here, and the math on that would be about 26 meters. And then the y component, or pardon me, just the last y component to add would be the 6 meters south. So I would need to make that negative since it's pointing in the negative y direction. The last thing I will do from there is I'll add together all my x's. So 15 and 5 gives me 20 meters in the x direction. And 26 meters plus a negative 6 meters gives me 20 meters positive in the y direction. All right, continuing the problem. So now I have the sum of all my components, all my vectors in both the x and y direction, and I'm going to now re-represent those. So that would mean that I'm going to have one vector to represent the sum of all my x's, and that would be a positive 20 meters, and a second vector representing the result of adding up all my y's, which again is positive 20 meters. And in blue, this represents the overall result, the resultant of all this addition. I need to find not only the size of this resultant, but its direction as well. To get the magnitude of my resultant vector, I would have to employ the Pythagorean theorem. Where A and B would be the legs of my right triangle that I've made. So that would mean that basically my resultant is going to be the square root of 20 meters squared plus another 20 meters squared, which comes out to about 28 meters. So I now have a magnitude for this vector right here. The last thing I would need to do is give my resulting vector some direction, and to do that I am going to use SOHCAHTOA again. So keep in mind that to give direction I need to have some sort of an angle to associate with my vector. It'll be the angle I just drew in this case. And I can then determine that angle by using the inverse of tangent. And I would just put in my opposite and adjacent side. In this case, it would be 20 divided by 20. And the inverse tangent of 1 would give us an angle of 45 degrees. So when all is said and done, the displacement for Johnny in our example was 28 meters with a direction of 45 degrees. Here's another example where instead of using a displacement vector, we use force vectors. So we have a stoplight supported by two cables, and these cables are separated by an angle of 50 degrees. Each cable is exerting a 10 Newton force on the stoplight, and the stoplight itself weighs 18 newtons. We want to verify that the net force acting on the stoplight is 0. So we know that if we want to determine net force, we need to make a free body diagram of the situation. And I'm going to draw in the different forces that we have. So the 18 Newton force I just drew, that is my gravitational force. And then we have two equal 10 Newton forces, and these are due to the cables. And the last little detail I would need is that the angle separating these two would be 50 degrees. Okay, so there's my beginning free body diagram, and now I will need to break those two cable forces into components, because if I go with a typical coordinate system, we can see that neither of those 10 Newton forces line up with solely our x or solely our y axes. So here we go. This will mean that, each of these are acting at an angle of 25 degrees from the y-axis, and that's what we just drew in here, which will allow us to draw in the components. So I'm drawing the y components in red and the x components in blue, so we can see what they look like. And of course, we can't forget about our gravitational force of 18 newtons at the bottom there. So what I will do now is I will get my x and y components for these forces up here, and then we will redraw this free body diagram with just the components showing. So now all of our forces will be in either the x or y direction. If we do such, this is what you would end up with. So we'll have a couple of x components pointing in either direction. Each one will be 10 times the sine of 25 in this case. And then we'll have a couple of y components here, and each y component will be 10 times the cosine of 25 degrees. So now it becomes much clearer to see that the y components of my two cable forces are going to work against the gravitational force of the stoplight, while the x components of the two cables are actually going to cancel one another out. So now we will, in our next step, actually add together all our x and all our y components and see, do we end up with 0 for our net force? Alright, so now that we have all our x and y components nicely laid out so that they line up with our coordinate system, which, to remind us, this is what our coordinate system is for this problem, let's make a grocery list. Let's see how all our x's and y's add up. So starting with the x direction, it looks like we're going to have a positive 10 times the sine of 25, which would be positive 4.2. We will also have a negative 4.2, which would come from this x component right here. And then in the y direction, we will have a positive 9 from both of these components here, and a negative 18 from our gravitational force. Keep in mind, these would all have units of newtons, since we are talking about force vectors. And our grand total would be 0 newtons in the x direction and 0 newtons in the y direction. So in this case, both of my components are 0 newtons, which means that my net force must be 0 newtons. Because if both my components are 0, that means my overall vector must be 0. So there you go, physicists. I've given you two heavy-duty examples where you need to break a vector into its components, then add up all the components in both the x and y axis, and then in some cases, recombine those components to get one final resulting vector. So till next time, physicists, until next time.